Hello everyone. In this video, I will briefly explain how I developed the regression model for the medical insurance cost prediction challenge. Our goal is to build a model that minimizes the mean squared error on the test data while also ensuring that the model is well fitted and not overfitting. So part one, uh, how I improved the model performance. First, I will explain the steps I took to improve the performance of our regressor. Well, part one is the understanding the data. The data set includes demographic and lifestyle information such as age, BMI, type of a child, smoking status, sex, and the region. The target variables we need to predict was the medical insurance charges. Those data set contain both the numerical and the categorical variables. Pre-processing became an important step. Two, building a pre-processing pipeline. Instead of manually transforming the data, we create a speed alert pipelines. For numerical features, we applied standard scalars. This helped the model learn more efficiently by normalizing the scales of the features. For categorical features, we used white-hot encoding. This converting categories such as region or smoker status into numerical format so that model can use them. It's a pipeline ensuring that the pre-processing and modeling are performed consistently and prevent the data leakage. Then is to choosing a stronger model. We initially consider a simple linear regression, but the insurance costs often have nonlinear relations with the features such as BMI and smoking. To capture these nonlinear patterns, we select gradient boosting regressions. This model builds an ensemble of decision tree sequentially, where each tree corrects the errors of the previous one. This usually performs much better than a single linear model for tubular datasets. And then, furthermore, improve performance, we use research CV. We count key hyperparameters such as number of trees, learning rates, maximum tree depths. Use a five-fold cross-validation to find the best combination of parameters. This step significantly improve the model's prediction performance and help us avoid choosing parameter arbitrarily. Part two is how we assess it and improve model fit. Well, first is the train validation split. We split the training data into training and validation sets. This allowed us to test the model on seen data before making final predictions. We evaluate the performance using mean squared error, which is the metric used in the global competition. This gave us the unbiased estimate of how well the model generalized. And second is the cross-validation. In addition to the validation split, we use cross-validation during the research. Cross-validation is important because it reduces risk of overfitting to a single train test split and provide a more reliable estimate of the model performance. Right. The third part is the learning curve analysis. To assess the model fit more deeply, we generate a learning curve. The learning curve compares the training data, training error, and the cross-validation error. Across different training data sets, it is very helpful for diagnosing the overfitting and underfitting, whether the data will help or not. From our learning curve, we observe that the training and validation error converged as the data sets increased. This sets the model achieved a good balance between bias and variance. Here's the learning curve. And finally, we did a final train on full data set. After validating the model and confirming good fit, we retrained the model using the entire training data set. This ensures the model has access to all available data before generating prediction for the test set. So in conclusion, to improve performance, we build a pre-processing pipeline and using gradient boosting regression, and then perform the hyperparameter tuning with cross-validation. To assess and improve model fit, we use a validation split and apply cross-validation, then analyze the learning curve. These steps help us build a reliable regression model with strong predictive performance. Thank you for watching.